Round of applause. Thank you very much. So indeed, I was an undergraduate here, undergraduate student, so it's a particular sort of honor to actually give this lecture, which is geared to undergraduates. And I certainly remember that when I used to go to colloquium as an undergraduate, I really understood nothing. It went fast, and you couldn't ask questions. You know, with Dave Jackson sitting in the front row, you didn't dare ask a question. So here, it's informal. If somebody has a question along the way, ask away. So my topic today is trapping and probing antihydrogen. And here you see a little cartoon of a trap with an H bar. I'll explain what antihydrogen is. And I'm doing this as part of the Alpha collaboration. And Berkeley has had a collection of graduate students, seen in red here, working on the experiment. And also, since there are undergraduates here, I want to point out undergraduates who started off with the experiment. That's Ariel, who's now graduated and is at CERN this year. But Crystal, Corona, who worked in Joel's lab before that, and other undergraduates here, Andrea, Robert is here now, Matt, Zach, and Carolyn may or may not be in the audience. So there's a lot of room here for undergraduates to play a role in both the experimental and the simulation aspects of antihydrogen research. Okay, so what is the basic idea? What am I going to tell you about? Everybody knows an electron moves around a proton, that's hydrogen. For each particle, there's an antiparticle. For the electron, it's the positron. And for the proton, it's the antiproton. And if you could manage to get a positron to orbit trapped around an antiproton, you would have antihydrogen. It's easier said than done. So in outline of the talk, I'll give you a little history of antimatter. How do we know it's here? Who discovered it? I'll give you some motivation why fundamental physics can be discovered by comparing hydrogen and antihydrogen. I'll give you an overview of what techniques we use to trap, something about the first measurements we've performed on antihydrogen, and something about our plans for the future. So the antiparticles. The first antiparticle was discovered, was predicted actually by Dirac, and this is, when you think of it, a rather phenomenal thing. The guy was looking at an equation, and he found a solution, and he wrote, a hole, if there were one, would be a new kind of a particle that had to do with the solution to the equation, unknown to experimental physics, having the same mass and opposite charge to an electron. We may call such a particle an anti-electron. And with that theoretical prediction, the whole field of antimatter began. 1931. Positrons occur in nature, so they're cosmic rays. I don't have a cloud chamber here, but I'm sure many of you have seen them. A proton, for example, might bombard the upper atmosphere and create a shower, and antiparticles will appear naturally in the shower. Here's sort of a schematic of it, and physicists build detectors down here to measure what comes down in cosmic ray showers and to try to understand something about the incoming cosmic rays, for example, their energy and their flux. Positrons also occur naturally. You all are positron emitters of one kind or another, as well as neutrino emitters. Potassium-40 emits positrons, naturally occurring isotope with a rather small relative abundance, but if you have a banana and you eat bananas, you'll have some positron emitters inside of you. So you're all radioactive. So, Dirac in 1928 predicted the existence of the positron. In 1932, Carl Anderson discovered positrons by studying cosmic rays, and basically he had a detector, and he saw tracks in this detector, and there was a magnetic field, and he saw that this trap is bending in the direction that it would bend, assuming that it was a positive charge and not a negative charge. Okay, and so by looking at this, at the curvature, he realized that this had to be the positron. His paper in 1933, the positive electron. There are also artificial positron sources that are used all the time. You can take an accelerator and transmute a stable element, so you can take one of the most potent, sodium-22, and that's used in positron emission tomography, so if somebody has some growth inside, or hopefully not a growth, in any case, something needs to be looked at inside, one way to do that is positron emission tomography. Some positron is ingested, it tends to sit in certain parts of the body, and then it emits, and people can see what's going on inside. That's from Wikipedia, so you can all look that up. Okay, so that's only one part of the two particles that are needed for antihydrogen. That's the positron. What about the antiproton? Well, the positron was discovered in 1932, and it took until 1955 when Segre and Chamberlain, well, here it says in Berkeley, they did it at the Bevatron. Does anybody know what the Bevatron is now? It's a parking lot. If you go to LBL to building 50 and you look down, there's a large parking lot on a flat area. That's where the Bevatron was. So these are there's Segre and Chamberlain.
And wasn't that the purpose for which it was built? It was built explicitly to discover the antiproton.
That's correct, yeah. And of course, with the machines were then built off, it discovered a slew of transuranic elements as well. So this was a great machine that went until the 1990s. This is a 40-year lifetime for this machine, discovering other elements as well. Okay, how did you announce the discovery in those days? Well, this is the World Wide Web in 1955. Progress of the antiproton experiment. But if you can't see it up here, this is actually the World Series score. So other important things were sitting on the board. And so here you can see what's going on. Here's a date. And I think somewhere in here it says, please don't tell anyone about this. But okay, so this is their board. 1955, when it was discovered. Another interesting thing is that this, nowadays you submit something to a journal until it goes out, it comes back. The whole process can take months. From the time they submitted this to the time that it was basically published was about a week. So people could be much faster. The turnaround time was much faster when you had a good result in those days. Now a month is considered incredibly fast. So you can broadcast things essentially at the speed of light, but you can't get them out of the paper that fast. So why should we study antihydrogen? Okay, so it's a fun thing to do, but why should we study it? What's interesting about it? Well, there's something I'll tell you about, which is the CPT theorem. So, and I'm going to tell you what it is, but let me just give you some background. So physical laws are identical in what are called CPT transformations. So since everybody says physical laws are identical, what that means is that we have a certain set of laws, and these laws are consistent with CPT. If you could find an exception to CPT, if you could show that CPT is not a good and invariant transformation, then you would, yes sir?
What's CPT?
I will go on, there are about 5 slides on that coming up. I just want to give you a little background to motivate the next 5 slides. So you want to search for an exception to CPT, and one way to do that is to compare hydrogen and antihydrogen and look at their spectrum. So look at their emission lines, say between the 1s and 2s, and if these lines are different, then CPT does not hold. And comparing spectra is one of the things we can do most accurately. We, meaning experimentalists, not myself. Spectrum of hydrogen is known very well, and any differences then disprove CPT. So what is CPT? Okay, the C, each letter stands for something. C is charge conjugation. Basically, it means take a particle and flip it to its antiparticle, keeping the mass the same. And if you do that, the laws of physics should hold. So as a cartoon, 2 positive charges repel each other. Take the positive charges, turn them into negative charges through the charge conjugation. And similarly, they repel each other. For those of you with a little more theory, and physics 7b is at the tip of your fingers, if you have F is equal to Q times E, for example, and you make Q equal to minus Q, you might think the opposite would happen, but no. When you change the charge, it means change the charge everywhere in the universe. So that electric field is made by charges. Those charges also have to be conjugated, and so Q times E is then invariant, and the force is the force. Time reversal, T. So let's look what happens here. Here you see one of these things. So this little ball is about to collide with that ball. That ball will then go this way and back and forth, and here's a little counter. So normally you have this mass is 3 times that mass as it happens, so you conserve energy and momentum. I'm assuming there are no losses. So here it goes, bouncing back and forth. And a mesmerizing motion. So now you can simply take this, and if you run it backwards, that is what time reversal means. the T of time reversal. What about P? P is parity, that's handedness. So I have a right hand and a left hand. For example, a right hand rule means you use your right hand. If you want to lose points on your exam, you forget that and use your left hand, and then you muck something up. Okay, right hand rule, parity is a mirror image. Okay, so parity transformation basically takes x to minus x vector, to minus x vector. And you can think of Maxwell's equations or conserved parity. C.S. Wu discovered that parity is not conserved, I mean completely not conserved, by the weak interaction in 1957. And this was a bit of a shock to physicists because it was assumed that the world didn't know the difference between left and right. Okay, so parity conservation essentially means that physical laws don't really care between left and right. What she discovered was that left-handed is not the same as right-handed. And this was a bit of a shock. And then it was said, okay, we'll take parity, but we'll do a parity transformation, then we'll do charge conjugation, and then everything should be okay. But that wasn't to be. Even though CP was initially thought to be invariant, it was found to be violated by Fitch and Cronin in 1964, but not by much, by about 0.2%. So one way of thinking of this is that if charge conjugation is switching black and white, and parity is switching left and right, then when you do both of those, you're going from one diagonal to the other, and that would be CP. But CP is violated. So now, if you add time reversal to get CPT, in answer to your question, CPT is a charge conjugation, parity transformation, and time reversal, all three of them together, you get something that will hold for a local relativistic quantum field theory. In other words, it holds for the standard model. And theorists don't have any widely accepted theories that break CPT. So a violation of CPT would be a major result, right? That's a good motivation. When you're doing something, you'd like to get a big result in it. And I think when you're doing things, you're young and you're going to do things in the future, look at the possible upside of your experiments as well as, the downside. Maybe it doesn't work, you can't finish it, something. But look at the upside. Is what you're doing something that could be significant, were it to be true? So here, this is a little bit of an extreme case of this. The probability that we find something is small, but if we find something, in the sense that nobody really thinks we will, but if we do find, but it hasn't been measured, so you don't know until you do it. But if we do find something, boy, that's a pretty big result. And of course, it probably wouldn't be believed, right? People would have to repeat it and so forth. But that's really, I think, part of the motivation here is that it's I'm a plasma person, so to work on something that has direct application to particle physics in this way, it's truly a lot of fun. Okay, another reason for studying antihydrogen is the Big Bang. So I think everybody knows what happens when a piece of matter and a piece of antimatter collide, right? Energy, okay? So the Big Bang should have produced, and you started off with energy, so matter and antimatter produce the photons. If you start off with all the photons, you're going to equal amounts of matter and antimatter, assuming CPT holds. So here's matter and here's antimatter. Imagine you start with this many pieces of each one. There's an annihilation, and lo and behold, we're left. There's something left here, which is just one piece of matter. So somehow or other, nature didn't start off with the same amount of matter and antimatter. And we don't understand why. It's in fact one of the branches, it's called the baryogenesis problem, is why when people look in the universe, people say, well, maybe there's an antimatter universe out there, but then other people argue that it's not consistent with astrophysical observations, that there would be, not a universe, but antimatter galaxies, antimatter stars, and people look for such things and they don't find them. Okay? So it's a mystery, and it's really one of the grand challenges of physics, and perhaps this will help solve the quandary. Another question, well, this is also related to that, is gravity. Okay, imagine I have an apple and I have the Earth, and as Mr. Newton knows, it falls. Imagine now I'm really robust and I have an anti-Earth and an anti-apple. That'll fall. But we can also ask the question, what happens when the anti-apple falls to the Earth? Well, okay, there would annihilate it. That's not really what I'm getting at here. The assumption is, and physical laws tell us, that an anti-apple should fall to the Earth exactly the same way the apple falls to the Earth. But who knows? Maybe the anti-apple rises instead of falls. Okay, that hasn't been measured either. So there are these things about neutral antimatter, because this is the first time anybody's made neutral antimatter. People have been studying antimatter in exquisite detail for charged antimatter. So things like the charge to mass ratio and the masses and the charges are known, but a neutral antimatter is not known, because it hasn't been made until the work I'm describing. Another reason to do it, well, you know, it's kind of cool, Angels and Demons, Star Trek, and if you allow me just to do this for a second. Since it's a small crowd, you know, in a big crowd I wouldn't have done this, but it's a small crowd, so just meander down here. Okay, slideshow, front slide. So this is the question, why are we doing this? Oh. Yeah, sure. Is there audio on this? There may or may not be audio on the projector. This is plugged in. This isn't. Oh, okay. So now, the loose wire.
I don't know.
I didn't know where to go. All right. This is what happens. You know, you're in a state school. When you're in a state school, you have to these things.
You can turn up the volume on your computer.
I'll turn it up, and if everybody's quiet, you may or may not. I'll turn this around also. Now I get nothing. Oh, because it's plugged in, that's fine.
Chemistry contains an extremely combustible substance called antimatter. We need to locate it immediately or evacuate London City.
I'm quite familiar with incendiaries research. Antimatter being used as such.
Well, it's never been generated in significant quantities before. It's a way of studying the origins of the universe, to try to isolate what some people call the God particle. But there are implications for energy research.
Particle?
Call it very important. It's what gives all matter mass, the thing without which we could not exist.
You're talking about the moment of creation.
Yes, in a way I am. The antimatter is suspended there, in an airtight nanocompacit shell with electromagnets of each end. If it were to fall out of suspension and come in contact with matter, say the bottom of the canister, then the two opposing forces would annihilate one another violently.
What might cause it to fall out of suspension?
Probably going dead. Which it will, just before midnight.
Kind of annihilation, how violent.
Cataclysmic event. A blinding explosion of about 5 kilotons.
I see.
Okay. So, one reason I showed this also was that the Segre lecture is on Monday. And you can see that in the movie, they conflated what's being done on the LHC, finding the Higgs and the God particle, with this work on antimatter. So they didn't really care about the correct details. Okay, so now I'm going to talk about what we're doing. Early history of antihydrogen. So, you know, we'd like to study antihydrogen. The first thing is you have to make it. It was first made at Lear in 1996 by colliding antiprotons with xenon. 99 more were made at Fermilab. Lear is a machine at CERN. And these were all going fast and they hit the wall. So it's nice to make them, but you couldn't study them. So it was not very useful. Then in 2002, Athena and ATRAP created cold antihydrogen. Cold meaning, you know, maybe, I suppose a few hundred Kelvin or something similar. One doesn't really know. But they couldn't trap them. And so Athena and ATRAP, Athena turned into our experiment, Alpha, and ATRAP is our competitor, led by Jerry Gabriels at Harvard. So what you need though is you need cold trapped antihydrogen to do spectral and gravity measurements. In other words, you need to have, as they had in the movie, you need to have a magnetic box. It has to be magnetic because it has to shield the antihydrogen from the walls. If the antihydrogen hits the walls, it doesn't bounce off. It's destroyed. So you have to keep it confined. And it's not hard to make it. So let me show you where it's made. So this is CERN. And this is the main site of CERN here. And in here, there's a small little ring. Let's see something there. There's a small little ring called the AD, the Antiproton Decelerator. And it provides a clump of antihydrogen, so antiprotons. The first thing is, why are we doing this at CERN? The reason we're doing it at CERN is that that's the only source of low energy antiprotons in the world. So antiprotons are made, but they're made by taking protons and hitting a target at high energy, spewing out high energy antiprotons that we can't possibly trap. So they're coming out at multiple GeV, multiples of 10 to the 9 electron volts, and we can't trap those. What CERN has built is a whole accelerator complex, maybe the size of 2 football fields, interior size, in which it can decelerate, slow down the antiprotons. It's a huge investment. They then bring us the antiprotons, and here you see where they slow them down. And the way they slow them down is they have electric fields that, they're coming in as a clump, you have an electric field pointing in such a direction that it slows them down. And they also have to cool them because they slow down. They would actually, their angles would get larger and larger, so they need to push them back on axis. And finally, they give them to us at about 5 MeV. And we're sitting in here. So here the experimental hall. So here's alpha. This is our experiment. Asakusa, the second experiment is here, and the A-trap experiment is up on top there. So the size of this is maybe 20 feet across, something like that. Yes, question?
That's not CERN, is it?
This is in CERN, yes.
Oh, no.
So this is not the LHC. This is the AD. Our experiment is not a humongous detector, as you might have thought from the movie. Our experiment is small. It fits across this room, essentially. And it's sitting in there. So here's a better sense of the scale. This is what's called the Berkeley solenoid sitting here. And inside here are the traps, the positrons. So we need 2 species. The antiprotons from CERN come here. The positrons are created in what's called a Serco trap. Basically, there's a radioactive source, and they come off the radioactive source. They're collected here. They're moved over to the mixing trap. The antiprotons are collected here. They're cooled, and then they're put together to make antihydrogen. So here's just another close-up. So what you see again, it looks like this. So here is the P-bar, the antiprotons. Here are the positrons. Here they're accumulated. We've then moved over here into this region, which is the mixing trap, where we create antihydrogen. But how do we know we have antihydrogen? We have to have a detector. So the blue is a detector which sits around the trap. So whenever an antihydrogen hits the wall, we can see it. So you see it makes pions, and you see the traps of the pions in the detector. So that's how we detect what we're doing. And the detector has both time and position sensitivity. So again, blowing this up a little bit, here is a maybe 10 to the 4, a few times 10 to the 4 antiprotons. Here are maybe 10 to the 7 or so positrons. Those are typical numbers that we use. How are they confined? So maybe if you see something, if you look at a picture like this, you might ask.
It's like P-bars.
P-bar is an antiproton. It's just, because the symbol for it is a P with a bar over it. So sometimes that usage leaks in here. But it's an antiproton. So you might ask the question, why is there a solenoid? Right? That's the first thing to look at, and why is it there? The answer to why there's a solenoid is that there's a axial magnetic field. The axial magnetic, so these are charged particles, remember. We have to make a neutral particle. And I'll explain in a little bit how we actually confine the neutral. But how do you confine the charged particles? It's not so easy. The way it's done is you have a magnetic field which is pointing along the axis. So a charged particle that starts to move off axis rotates around the magnetic field line. So this magnetic field traps particles transversely. Okay, and similarly there's a magnetic field in here. So the transverse magnetic field, the longitudinal magnetic fields provide transverse confinement, but how do we manipulate things longitudinally? How do you get a clump of antiprotons, which are negatively charged, and a clump of positrons positively charged to overlap? How do you move them along the axis of the machine? You do that by having many, many electrodes, each one of typical this dimension is about 2 centimeters, and that's about 2 centimeters in size, and these things are actually blown up. They're more like some millimeter in size, both of them. But what you do is you change the voltages. So these voltage things come out here. You change the voltages, and by changing the voltages, you can take one species and kick it to the left or to the right. So when you do that, you can then control these two species. And essentially, a couple of million commands are required in the mixing process that we use. This is a cartoon. Here's a picture of the actual device. So here's each of these corresponds to one of these rings. So here you can see part of the conundrum. These are called Penning-Momberg traps. And this is the axial position, so along the axis. The positrons and the antiprotons are going to want to sit one at a low potential and one at a high potential because they have opposite charge. So I can't make antihydrogen unless I overlap the antiprotons and the positrons. So that's going to require some amount of trickery to do that. And let me say, so if you had listened to any of these talks prior to 2010, we started this in around 2005, you would have heard that it's difficult, it's hard, various reasons of why we haven't actually trapped anything. So I'll just explain it in some simple scaling arguments. So antiprotons are created at 1.7 GeV about. The self-potentials in the plasmas, so that's just, you have charges and you move out radially, you get to about 10^2 volts in self-potentials. The depth of our neutral traps, I haven't said yet how we trapped I said we had a magnetic trap, I haven't said what kinetic energy you can trap. It turns out that our kinetic energy is, our trap depth, which is governed by the magnetic field strengths we can reach, is only about 40 micro electron volts. Okay? So here you have potential energies which are much greater than allowable kinetic energies, and you're manipulating these things, and if you convert potential into kinetic energy, you end up in a lot of trouble. And the amount we cool by is...
What did you just say? If you convert what to kinetic energy?
Okay, so if you have so the self-potential, so you have that clump of charge. And if you look at the potential difference between the axis and the radius of the clump, depending on parameters, you get numbers which are of order, say, 100 millivolts. Okay? 100 millivolts is, so 1 volt is 10 to the 4 Kelvin. So 100 millivolts is 10 to the 3 Kelvin. Okay? So you have 1,000 Kelvin in potential difference.
Yeah.
But the allowable kinetic energy is only half a Kelvin.
Yeah.
The temperature of your plasma is governed in part by the walls. So the walls are cryogenic, you're cooling the walls down, the particles radiate, so you cool the walls with liquid helium, the particles radiate, so there's cyclotron emission. In principle, they should go to 4 Kelvin. They don't, that's another matter, but because there's noise and other problems, they only go to maybe 10 Kelvin at best. So the plasma itself, the kinetic energy should be maybe 10 Kelvin inside the plasma, so the particle kinetic energy, which is much less than the potential energy. But now I have to take this glob and I have to move it. So I'm doing something dynamic. When you do something dynamic, there's some chance that you're going to take some of that potential energy and convert it into kinetic energy. I'll show you a cartoon of that happening in a minute. When you do that, it means you have something too hot to make trappable antihydrogen.
Yeah.
So part of the goal here is to make something you can trap. Oh, this is just for fun. So the antiproton creation energy divided by the trap depth is 10 to the 14. If you compare that to the LHC energy increase, that's 10 to the 8. So we're actually slowing things down in some sense more than the LHC accelerates them. But the real physics issue is that the collective potential, that's the self-potential here, over the trap depth is 10 to the 3 to 10 to the 5. Okay, so what's our recipe? We take about 10,000 antiprotons, we cool to several Kelvin, we take about 10 million positrons, they're cooled to the same temperature. We mix, keeping the species cold and confined. And okay, this is sort of an advertisement for those of you. What techniques become important? I won't read off the details, I'll just say it. You need to know something about atomic physics for the recombination, particle physics for the detectors, cryogenic physics, and beam and plasma physics. So it's a truly interdisciplinary thing, which everybody says is disciplinary is good. The funding agencies say it, and the reason they like it is that then somebody else will pay. So, all right, so how do you capture these antiprotons? They're coming in here at 5 million electron volts on the left. They hit a thin foil, that's the name of it, we call it a degrader. In here, trapped is a little small electron plasma, which is cryogenically cooled. So this electron plasma might be at 10 Kelvin. These are coming in. So we can, and it turns out that we raise this potential here. I'll show you a picture. So you raise the barrier on the left side. You trap anything less than 5 Kelvin. You lose 99.9%. So you're getting about 10 to the 4 out of 10 to the 7. 0.1%. And then these guys come back and forth, and you raise the potential on the left, like this, and now you've trapped something at 5, with energy less than 5 kilovolts, and it cools off the electrons through collisions. Okay, so it's basically the antiproton is heavy, and it's moving fast, and the electrons are light, and they're very slow, and so the antiprotons plow through the electrons, giving them kinetic energy and cooling down themselves. And they do that for some length of time, and then they cool. Okay, so about 20 seconds to cool down. Okay, so now I'll just show you a picture of the business end of the trap. So this is an antiproton is coming this way, the positrons are coming here, the antiprotons have been cooled, and now this is how we make our actual trap. So we have to make a magnetic minimum, and I'll explain that in a minute why, but I'll show you what it looks like. We have to, so there's a longitudinal field here, which is needed for the charged particle confinement. But once the charged particles combine, you get a neutral particle, antihydrogen, which then is not confined radially, because it's radially by a constant magnetic field. You need to define it by a magnetic field gradient, and to do that, we have this octopole coil in red, and mirror coils in green. And here you see what happens. We find a way to take the antiprotons before injection and then inject them so that they're overlapping the positrons in here in this region and making, hopefully, antihydrogen. Okay, so how does that work? Imagine you had antiprotons here and positrons here, and you say, okay. Remember, these are trapped in a well down here, and this is like this. So you just say, okay, I'm just going to raise this up. Then they'll just bounce like this. So you can do that. They bounce back and forth. Here are the positrons. Now remember, this is on the vertical axis, voltage, okay, energy. They're overlapping spatially, and these positrons are cold, and so the antiprotons internalize with the positrons. They'll cool down like this, and they'll make antihydrogen. If you do that, we can make, without any problem, 10 to the 4 antiatoms in a shot. So we can make up to roughly half the antiprotons can be turned into antihydrogen. The trick is to get antihydrogen that's cold enough to be trapped. And it turns out that when you do this in the usual way and thermalize after mixing, you don't get antiprotons that are cold enough that when they make the antihydrogen, you can trap anything. So we had to use a new method for trapping, which is injection, so injecting of antiprotons into the positrons via something called autoresonance, which is a fun little piece of basic physics that I think everybody with 7A can understand. So it really, now forget about the charged particles and just think about a pendulum. So a nonlinear oscillator will, under some circumstances, so it'll adjust its amplitude. The nonlinear frequency matches its drive frequency. That's the concept. And it's so those of you who know about it, it's the extension of something called phase stability. It's been seen in many phenomena, right? How does it work? Okay, so here, play the movie. On the left is a pendulum, and it's being driven resonantly. So here you see the amplitude of the pendulum. There's a drive frequency exactly on resonance. That's what one means, but the pendulum, because as it gets to a higher potential, higher amplitude, its frequency changes, its amplitude grows, and then it decays. And so you all know this, somewhat on a swing, that when you're on a swing, you want to adjust the rhythm so that you get to the maximum amplitude. Otherwise, you're off and it doesn't work. Okay, so this is what happens with a constant drive on resonance. Will just go up and down because of the nonlinear frequency shift, that at higher amplitudes of oscillation, the frequency is low. So now you can do something different. Now we're going to do autoresonant drive. So now the drive frequency is not at 1. The pendulum hasn't really moved. Its frequency is 1. The drive frequency is decreasing. When this drive frequency hits 1, then the pendulum should really begin to feel the drive. So it's now approaching 1. And so you have basically a chirp drive. So you're kicking this thing with an ever decreasing frequency, but it's decreasing slowly. And now you see a big effect as it comes to 1. And now a very interesting thing happens. Assuming you set up your parameters correctly, the pendulum naturally syncs itself to the drive. That's the autoresonance. So you don't do anything. And if you're doing this slowly enough, with enough amplitude, but not a lot, you will sync the pendulum to the drive, and then you get a very large amplitude of oscillation.
Wow.
Okay, so that you can all try this. You can just write down a differential equation and try it yourselves. You might imagine, so this is one particle, right? So you have a particle in that potential well, it's going back and forth. And there, all the way at the top, right? Okay. I'll just show you what happens when we do our injection autoresonantly. So this is a cartoon, it's an early version of the simulation that we're actually, my graduate student wrote, jumped in cell. So here is a clump of 10 to the 4 antiprotons in its well. The positrons, not shown, are sitting in here. It's autoresonantly accelerated. Here's this clump moving, but it's staying as a clump. It gets to a larger and larger potential. It's going around here. And remember, you don't see the positrons, but they're in here. That's just a glitch. And here they come spewing off. And the ones, if you have enough of them here at low energy, and there's also some cooling from the positrons, you can make trappable antihydrogen. So, here's the trap again. Here's the magnetic field. Here's the magnetic field here. This is the well. So now this field makes a field magnitude that has a minimum on axis. You see that down here. And if you want to see what happens, well, just there's a dipole moment associated with the antihydrogen. And I can play this. It's just like having a bar magnet, which is confined to be along the field lines like this, and so it bounces back and forth. Okay, in view of time, is a nice movie of the whole process, but I don't think I'm going to show. Let's see. When do I have until 5? Then I'll show it. Everything I said, if you kind of were sleeping and spaced out, you get to see it again. Okay? This was a freebie movie of the mixing process. This group did it. So this is our detector. It has 3 layers. And soon they're going to peel out. So here are the 3 layers. So we need 3 layers so you can look at invert the tracks. Here's the octopole, the mirror coil, it's the annihilation detectors, and the other mirror. So here's the energized, the currents running in this thing. So here are the currents running. It doesn't show going around here. And there should be another arrow over there. So here we have an energized trap. And now you're going to see what happens when you look inside here. So here are the cylindrical electrodes that I described that are used to control what happens to the particle. So here's the potential. This is the potential as a function of position on axis, p bars and p pluses. And we slowly excite it. And soon this will move over to here, and then you'll see the formation of antihydrogen. Because each of these clumps are 10 to the 4 and 3 10 to the 7. So the antihydrogen is formed with a three-body collision. You can't make antihydrogen without either a p-bar, a positron, and a photon, or two positrons, and this is made by three bodies. So here you've made an antihydrogen, and now you do something to it. So part of what here it is bouncing, again, that's that potential well with a little more pretty graphics. It's confined. To see if you have anything, what do? Well, you turn off your magnetic fields, the transverse fields, turn this field and that field off. There it goes down. Now your antihydrogen is not confined, it hits the wall. Pions are made, it hits the detector, and you see tracks coming out. Then you have an algorithm that inverts the tracks, and you can see that you made something. So that's the idea for the construction of antihydrogen. Okay, so we did this in 2010, trapped antihydrogen. Got a lot of publicity. If we deserved all the publicity we got, it didn't hurt us. A lot of publicity. Then about 6 months later, we published that we could confine it. So this first confinement was only done for about 1/6 of a second or so, mainly because we wanted to go long enough that we were sure we'd be seeing something that was antihydrogen, but we didn't want to wait a long time because we wanted to try again if it didn't work. So here we went for 1,000 seconds, Nature Physics, and this was ground state, and that's required for spectroscopy. And now, most recently, and I'll tell you a little bit about this in more detail, on Nature, we had the resonant quantum transitions and trapped antihydrogen. I'll explain what that is. So it shows that it's possible. So understand what we're doing. We have 10 to the 7, so we start off with 10 to the 7 antiprotons. From those, we make 10 to the 4 that we can catch. From the 10 to the 4 antiprotons, we make maybe half of those. A few 10 to the 4, we make 10 to the 4 antihydrogen. Of the antihydrogen, we can trap 1. Okay, so we're starting off with 10 to the 7 antiprotons, and we make 1 antihydrogen. Now, making 0 is very bad. Making 1, evidently, is enough to do good physics, and I don't think we appreciated that. Well, when you're doing something for the first time, it's easier to do good physics, right? But down the road, we have to do better than 1. But nevertheless, you can do it with a few antiatoms. So this paper was done with just hundreds of antiatoms is all we can. Trapped antiatoms. Of course, we'd really like to have 10 more. So the result is that our trapping rate is about 4 per minute, 4 per hour. Okay? So it takes about 15 minutes to go through a cycle, and we get 4 of them. If we get 1 a minute, that would be much better. So 60 an hour. And we might be able to. We're building a new trap. So I'll just show you. This is just a nice cartoon. Those of you who've taken the 137, and so you know. So quantum mechanics, this does not look like a typical atom. And the reason is there's a very strong magnetic field. So when you make a magnetic field, when you apply a very strong magnetic field and you're making a very high state, the Larmor radius can be smaller than the trap distance between the antiproton here and the positron out here. So when that happens, you make what's called a guiding center atom that was explored by Glinsky and O'Neill in San Diego. And this will then decay over a period of a second to the ground state, and then you have a ground state atom. But it's sort of an exotic thing to start off with. We don't have evidence. I mean, this is theoretical. We don't actually measure what state it's in, but if you do the theory, then that's what you get. Okay, so what did we do? So we have, I went a little too fast there. Here's the same picture I showed you twice before, except now we're going to add microwaves. So there's a magnetic field. There's a trapped antihydrogen here, trapped in here, in this region where the field is rather uniform, and we send in microwaves. Okay. And so now the ground state of hydrogen is split by the hyperfine splitting. That's a 21 centimeter line in astronomy. Then you have Zeeman shifts. Okay, and the red states are states that we can trap, and the blue states are what are called high field seeking states. So the positron spin has opposite alignment, and they're not trapped. So if we can induce a transition from a red state to a blue state, that trapped antihydrogen, and this is in the microwave region. This is in the gigahertz range. So if we can induce a transition here, then what we've done is we've flipped the antihydrogen from something which will stay trapped to something that won't stay trapped. Well, basically, you have something in a cage, right? That's our trap. And you can do something to it. If you do something to it that makes it hit the wall, you can see it, because we see each and every one. 60% efficiency, more or less. So if we do something to it and we see that we did something, then we know we've done something interesting. So you could, but this is a specific frequency that you're hitting here. So we can send in microwaves at this frequency or this frequency, and we can see if that anti-atom, if something happens to anti-atom or not. They have to be a little bit tricky because we don't know for sure that we have an anti-atom in there. So you have to be, the statistics have to be done properly. So you have to do null tests. So here is resonance width. So this is the resonance width having to do with the magnetic field. This is the splitting. This is frequency. You send in the microwaves here. So we can send them in at this resonance or at that resonance. And look what happens. So here I'm just going to show you the results of the experiment. So these are, we did 2 sets of experiments. I'm just going to tell you one set. So these are events every 15 seconds. And so this is time coming in here for 3 cases. When we're on resonance, when we're off resonance, and when there's no microwaves, which is control. Okay, so the idea is there are 3 things you'd like to do. So if you're on resonance, then you see that in this region where you put in the microwaves here, you get a big signal. Okay, this is a cumulative event. So this is for all our data. If you're off resonance, you're sending in microwaves, but they're not at this frequency. They're at the wrong frequency. You get the blue, and if there are no microwaves at all, which is more or less a control run, you get the red. Okay, so we're looking to see when things hit the wall as a function of time over a period of about 4 minutes. And here you can see that during the time when we're putting the microwaves in on resonance, we get a very large signal. So that tells us that we're hitting it. And we narrowed it down to part in 10 to minus 3. Similarly, we can correlate with axial position, and a similar thing holds. Okay, so now I want to say a word about gravity, because I did mention gravity. It would be kind of interesting to see what happens to antihydrogen. It turns out that, so gravity is a very weak force. But if you have a potential here, so this is our potential. So 0 measures time from when we turn off that magnetic field potential. Okay, and we turn it off with an e-folding time such that it's very small by 30 milliseconds. The effective gravity here, so then this axis is the vertical axis, even though it's horizontal. Okay, y is vertical here because z is axial in accelerator systems. So y is the vertical axis. This side, the low side and the high side are identical. So the effective gravity, this is the effective potential that's seen by the particle, is pretty small when the magnetic field is at full strength. As the magnetic field weakens and weakens and weakens, note there's a big if here. If you assume that the gravitational mass of antihydrogen, so I'm going to break the weak equivalence principle hypothetically, is greater than its inertial mass by 100 for every particle we know, and for the weak equivalence principle to be true, this has to be 1. But to get a sense of the sensitivity of where we are now, were this 100, then in 30 milliseconds we could see things roll out. Okay, we could distinguish, 100 from say 1 or something, or we could exclude 100-ish. And so this is an example. So the only way you can do that, I won't go into the details, we're running out of time, is to do an awful lot of simulation work. So you can do simulations in which you compare various hypotheses. You compare the normal case where the gravitational inertial mass is the same to the case in which the gravitational inertial mass has some ratio. And then you look at these things and you can make comparisons. It's a good place for undergraduates actually to contribute.
Annihilation.
Pardon?
That's not annihilation. It's like when they annihilate each other.
Yeah, so, what?
That's not annihilation.
And the y-axis.
Oh, yes, thank you. So this is the time at which they annihilate, and this is the position in which they annihilate, vertical position in which they annihilate, and this is a cumulative. I didn't want to get into details. This is a cumulative distribution.
Yeah.
So this is the sum of the y's at which you would annihilate. And what this shows you that if that ratio were 100, which there's no evidence that it is, but hypothetically, okay, if it were 100, you could see it in our kind of experiment.
Yeah.
Okay? Okay, so at this, our rate, so we're making it 10 to 50 Kelvin. Our trap depth is smaller. We only trap the coldest ones. So as I said, approximately 1 out of 10,000 anti-atoms is cold enough to be trapped. So here we are, 10 to the 7 antiprotons, 5 10 to the 4, so captured and cooled, a few times 10 to the 4 antihydrogen produced, and 1 captured. And all that takes 15 minutes. So our goal is for the future, this number goes up at least by a factor of 10. We have much greater understanding of our magnetic field systematics, and we have laser access to our machine. So we're rebuilding our machine, and they're actually, we have my graduate student Captain So is there now, and Ariel Little is there, also working on the experiment, as is Joel Fajan, Professor Fajan. So here you would have a solenoid. We've separated the capturing trap from the mixing trap for various reasons. In particular, we'd like to have a reservoir of antiprotons here, so we have to share this experiment. So right now there are 3 experiments. We may have to be sharing with 4 or 5. We'd like to be able to run all day long. We don't mind sharing, but we'd like to still run 24 hours a day. And to make that consistent, if we can make a reservoir of antiprotons we can hold on to and just release the ones we need to make antihydrogen when we need them, then we can operate beyond the 8-hour shift that we're getting now. So that's one reason. So we want to make a reservoir of antiprotons here and then separate out the magnetic trap region, which now has access to laser and microwaves, better diagnostics, and it was funded by Carlsberg, the beer company. Okay, so when you drink a beer company, you can know that, this is our favorite beer. I guess Carl's, the story, well, no, there's a story, but I'll tell it after the camera's off. So neutral antimatter science, then this is the end. What are our plans? So it's under development. So it's installing now, next year, characterizing in 2014. We're going to explore the advantages and utilize the advantages of being able to do very careful comparisons with simulation and the fact that we know when we do and do not interact with the particle. It incorporates, of course, the many lessons that we learned. Hopefully it incorporates, hopefully we learned the right lessons, right? You could run too fast and end up being behind. But okay, enhancements, laser access, separated capturing and mixing traps, improved diagnostic, enhanced detector, stacking of antiprotons, and maybe antihydrogen. Below that cutoff, you don't have to worry about it. And physics studies 2015 to 2020. So that's our plan. We would love, so where, do I actually say, do I brag for what we want to do? Oh, I did say something, okay. So CPT, 1s to 2s state, and microspectroscopy, gravity, and charge neutrality are just 3 of the things we'd like to be studying in those 5 years. And we'd like to get to, so as a goal in 5 years, it would be great to get to at least a frequency resolution that's been achieved in the kaon studies, which are the best to date. Here, if we're very, very lucky, we get to say if it falls up or down, Newton or anti-Newton. And charge neutrality, we hope to do a better measurement of charge neutrality than other people have done before. Okay, meaning we hope to get a better measurement of the positron and antiproton charge than people have before. That's it. Thank you very much.
All right, so now we'll have a few minutes for questions and answers.
Ask away. Is that camera still running?
Yep.
Still running.
Still running.
I don't know if that's good or bad.
Stop it.
You can keep it going. That's right. There's yes, sir.
Is the alpha apparatus at Berkeley?
Is what a person?
Is alpha at Berkeley?
No, alpha's at CERN, but we have so that all this stuff has to be done in Geneva because we don't have antiproton. The antiproton, the first antiprotons were made at the Bevatron, which is now a parking lot.
Oh, right.
Okay? So that parking lot isn't going to help us. CERN has been very, if you will, very willing to get involved in low energy antiproton physics, unlike what's happened in the States. So they actually have the only facility in the world for doing this. So if you're going to make antihydrogen, you have to do it at CERN. And there are about 4 groups. I showed you 3 experiments, but there's now a 4th and a 5th. Yes?
Alpha is an acronym. What does it stand for?
Say again?
Alpha, what does it stand for?
Oh, antihydrogen laser physics apparatus, which is a little bit funny because we actually don't have laser access now. So alpha 2, well, the name is good, but we didn't put it. The goal of the first alpha experiment was actually to see if we could trap, because we didn't know if these techniques would work. And I didn't get into the plasma physics along the way. Undergraduates don't really study plasma physics very much at all. But a lot of what was done, so this was understanding how those collective effects can be used and play in, and how you need to control them. We use rotating walls to compress these plasmas. The autoresonance is working, and it's interesting, and nobody asked, but it works with a collection of particles. I showed you this, the pendulum, right? But you might ask the question, well, if you have a collection of particles, that's the 10 to the 4 particles, why should it work when they're all running around in different phases? And it turns out that the fact that it's a plasma and there's space charge makes the autoresonance work better than if it wasn't there. So that's sort of that was discovered by some colleagues of ours in the Hebrew University, and that works. So that was one of the important things. Yes?
Why does the non-constant magnetic field work better to confine these than?
Okay, so basically the force is mu dot, the potential energy is mu dot B. So magnetic moment dotted into magnetic field. Okay, and the force is the gradient of that, and mu is constant. So basically the force is proportional to the gradient of the magnetic field. Okay, and that brings me to so there's a demo in here that I didn't show because my colleague, Professor Fagins, who's an experimentalist, said that it took him half an hour to get it set up, which means that he was setting me up not to have it work. So I didn't do it. Has anybody seen the levitating top demo? So the principle that it's going to work, so this is magnetic. You would take a top here and spin it, and you would lift this up. Okay, let's spin fast enough. This is YE. All right, we can play with it afterwards. I actually have a launcher for it, but I don't want to waste time now. If this is spinning, so when this spins, it forces so basically what happens is that when you see here, this wants to flip over, right? This is magnetized, this is magnetized. When it spins, it can't flip over because of angular momentum. And so, all right, I won't try again. But you'll see that it can then levitate. So you can lift this up a little bit, move this out, and this top will just be spinning down, not touching the ground. Okay, and you can probably find that on YouTube, but this is the principle by which we travel. Okay? Yes?
So right now you have a sensitivity that's kind of 100 times the mass of the proton, the gravitation, the inertial mass.
Well, I can't formally say what our data says, but
more or
you
less.
could imagine
Right.
that.
So what I want to get at is to see whether antimatter falls up or down. You need to do better by a factor of a few hundred. And
Yep.
at that point, will you be limited by the precision of the fabrication of the octopole? As the octopole field turns off, how do